So this is our second lecture in Chapter 3 dealing with one-dimensional steady-state conduction. We covered the plane wall and radial systems, and we especially emphasized that resistance concept. R for a plane wall is L over Ka, and then we also developed it for a cylinder and a sphere. That was summarized in this section 3.4. Now we move into a section dealing with energy generation. So we have conduction with thermal energy generation. It's still steady state and it's still one-dimensional. Think of a slab of thickness 2L, so it's just a planar system. Often you put the CL. Hey, what does that CL stand for? Center line. So we have the center line, and then our thickness is 2L, so we're going to have our coordinate system X. Put X equal to 0 plus L and minus L. That's common throughout this textbook. You have the material of thermal conductivity K, and it has uniform heat generation, so it has a K and a Q dot. Now that Q dot is watts per meter cubed. That's our volumetric heat generation. How did it come about? It just came about. Electrical, chemical, nuclear, something liberating and transforming into our energy balance. So at this surface, they have Ts is the value at X equal to negative L. And over here, they have the same surface temperature, Ts, at positive L. Solve for the temperature distribution in the wall. Find T as a function of X. How am I going to find T as a function of X? You forget you're a mechanical engineering major, you think yourself as a mathematician, and you just set it up and solve. What are we going to set up and solve? Our heat diffusion equation. Yeah. And so it'd be something like, how about I pause and walk around? I want to see if you can write from memory. One-dimensional, steady state, heat diffusion equation, rectangular, just X, right? But you have the Q dot. You have that volumetric heat source term. All right? As a little hint, what was our starting heat equation for the plane wall? You remember that? And then when we had for a cylindrical, remember that? And then for spherical, remember that? But now we're just saying a plane wall. There's a big hint right here. Hey, that was the one-dimensional Laplacian, wasn't it? Yeah. But without looking at any equation sheet, can you tell me what is my governing differential equation that I'm going to solve with two boundary conditions, and I'm going to solve for T as a function of X? All right, so our heat diffusion equation comes in at K. The second derivative of temperature with respect to space squared, that's our Laplacian, plus Q dot equal to 0. How many agree? You like that? Is that good? So then we have that T at X equal to minus L is equal to Ts, and then T at X equal to plus L is equal to Ts. Now, before I solve it, if I plot T kind of in that Y direction, these have the same height. What do I expect my solution to look like? Parabolic. Yeah, it's going to be parabolic. Now, will it be shaped like this or shaped like this? The first or the second? The maximum temperature is going to be located where? At the center. Right? Now, somebody says, oh, that's too easy. Change it up. Okay, call this TS1 and TS2. Different temperatures. They're not symmetric anymore. Which one do you want to make greater than the other? Do you want TS2 to be greater than TS1? All right, let's put TS2 right here. This is TS1. Let's make TS1 greater than TS2. Leave this one to be TS2. All right. What happened to my temperature distribution? Is the maximum still in the middle? Right smack in the middle? Or will it be moved where the maximum is over a little bit to the left. Yeah, that's what it's going to do. True? So you'll have the maximum right there, a little bit to the left. The math will work itself out. Let's go look at the next slide. Hopefully I have it there. Sure do. So I have T1 and T2, a little more general. How do I solve this differential equation with two good boundary conditions? Separate, integrate twice. You get two constants of integration. You then apply your boundary conditions to solve for them. And it looks like this. And when it looks like that, what do you say? It looks like this equation. This is y is equal to, I don't know, ax squared plus bx plus c. Did you learn it that way? Yeah, that's our old friend. And so we can see, oh, that's what a is, and then b, and then c. But then you remind yourself, here's what they all are. You remind yourself, what does that look like? What's that quadratic equation look like? In this problem, our a's are always going to be negative. It's always going to be concave down, never be concave up. And you remember where that maximum is. How did you get that equation, minus b over 2a? You can differentiate and then set equal to 0, and then you'll find that maximum is where the slope is equal to 0. And this is something really handy to remember. So here's your b and then your a. What you find is that it can shift over here if this temperature T1 is greater than T2, or it can shift this way if T2 is greater than T1, wherever the maximum temperature is, on the right or on the left. All right, so that's our old friend, the parabolic equation. That's our solution. Here I am explaining it again. What are the roots? Minus b plus or minus, remember this one? Square root of b squared minus 4ac divided by 2a. Did I do that right? And then this is the next most useful. This is, everybody kind of remembers this quadratic equation. A lot of people will forget, oh, minus b over 2a is where the maximum or minimum is. In this case, we're always looking for the maximum because it's concave down. But it could be concave up, and then it would be the location of the minimum, as shown here. So good review of the quadratic equation. Half of engineering is difficult because of the math. All right, let's move on. A wall of thickness 2L. So if it's of thickness 2L, its half thickness is L, and we typically run X from negative L to positive L. All right. Has conductivity K and uniform heat generation Q dot. The temperature is Ts at both X equal to plus L as well as negative L. Ready for a clicker question? Let's take a look. How will the temperature profile change if Q dot is increased? So Q dot goes up. Will the location of the maximum temperature move toward the right, increasing X? Or will it move toward the left, decreasing X? Will it increase the surface temperature, Ts? Will it decrease the maximum temperature, which is located at X equal to 0, or increase the maximum temperature, which is located at X equal to 0? So, we have a distribution of results. Okay, most people are, what is that, 60% of the class is correct. The maximum temperature will stay at X equal to 0, but it'll go up in value. Actually, if I plotted that quadratic equation, if Q dot gets smaller, 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 actually in the limit Q dot goes to 0, it's a flat line. And then Q dot increases, it goes up a little. Q dot increases, goes up a little. Q dot increases, goes up a little. But the temperature, the boundary temperatures are fixed at Ts. That was a mathematical statement. So as Q dot increases, the quadratic equation is more severe. Okay. So that was our right answer. Some people may think, well, it's got to affect the boundary condition, but that's what's fixed in our mathematical solution. Okay, same thing, wall thickness 2L, conductivity, and Q dot. Temperature at plus and minus L is the same. How will the heat flux at x equal to plus L change if Q dot is increased? So we have our slab and we have Q dot generated throughout, and then what we're interested in is the Q double prime, that's our flux, at x equal to plus L. How will that change as Q dot goes up? All right, let's go ahead and stop. So this temperature profile is always symmetric, isn't it? And so here, so if I said, is Fourier's law still applicable? Is Q double prime equal to minus K dt dx? Is that still applicable? Sure, it's still applicable. Okay, what that says, if I look at dt dx right at the center, it's 0. But a little skosh to the right, it starts to go down, down. And as I move further out to the right, all the way, isn't it steeper, steeper, steeper? And so what happens is the steepness of that curve multiplied by the thermal conductivity is the flux. And if I'm leaving that surface temperature there and I'm increasing Q dot, did it become steeper? Sure. And so there's a greater transfer out, more flux. Okay, there's a number of ways to maybe another way to explain this is all of the heat that's generated in this side has to exit through that door, through that wall. All the heat generated this side has to exit through that wall. And so as the amount of heat generated goes up because Q dot's going up, there's a greater flux out the walls. So it will increase. Let's grade this. So I don't know why. Maybe you just like my English. Remain unchanges. What? Unchanged, sorry. Let's look at the next one. How will the temperature gradient at x equal to L change if Q dot goes up, if Q dot is increased? Will it increase? Will it remain unchanged? Or will it decrease? Now, what I'm going to do is I'm going to do this. I'm going to modify the question. I'm going to say the absolute value of that. Okay? I want the magnitude of it, the absolute value of it, because we just talked about a negative sign. So the results show that yes, the magnitude of the temperature gradient goes up. Now, it's one of these where it was like this, then it's like this, then it's like that, which means that it's larger negative slope. But I didn't want you to get confused on the negative. It would be maybe for the first one, it's maybe negative 5 degrees C per meter, then negative 10 degrees C per meter, then maybe negative 15 degrees C per meter. Okay, in that case, it's a decreasing, but the magnitude, then it's just like that. All right, let's press forward. All right. We have a temperature distribution in the wall. And so this is minus L, this is plus L, that's x equal to 0. This is the x-axis. This is temperature plotted up, and T1 is different than T2. Can you see the numeric value of T1 from the plot? 50. What is the numeric value of T2 from the plot? 20. So there's 50 and 20. Ready for some questions? Let's take a look at this. So the heat flux at x equal to plus L is in the positive x direction equal to 0 or in the negative direction? What is the direction of the heat flux at x equal to plus L? Correct. We'll stop. So remember this law. Q double prime is equal to minus K dt dx. And what do I often forget? I often forget that negative sign. And so here dt dx is negative, but I multiply by a negative negative sign, and then the conductivity to get the positive heat flux. Heat always flows hotter to colder. It's flowing out of that slab at x equals 0. So it's in the positive x direction. Let's go ahead and grade. All right, next question. The heat flux at x equal to negative L, we're focused now over here, is in the positive x direction equal to 0 or in the negative x direction? And let's take a look at the results. So it's in the negative x direction. Actually, it's flowing out in the positive direction at x equal to plus L, and it's flowing out of our system, out of our slab, meaning it's going in the negative x direction at x equal to negative L. Okay, what is the heat flux at x equal to, what does that say, negative 0.1 meter. So if I look at negative 0.1 meter, I come up right here. What is the heat in the positive x, 0 or negative x direction? And so let's grade that one. So it is flat right there. That's why we picked it. It's flat, and because it's flat, the derivative is 0. So this term is 0, and I should have put don't forget the negative sign. But anyway, let's do the last one. Okay, at x equal to 0, which is the center line at this location, what is the direction of the heat flux? Positive, 0, or negative x? And we'll tally up the results. And one person came in at C. I don't know how. Well, they were trying to get to A, and they missed it. All right, so here, let's move now to a solid rod, and it has that internal heat generation, that Q dot, and let's just pick an outside surface temperature, Ts. Well, you start with a differential equation, two boundary conditions. Does the differential equation look good, first and foremost? Yeah, it's at K times the Laplacian of the temperature, 1D, cylindrical. So they put the minus Q dot divided by K over on the other side. You're ready to separate, integrate. Look at the boundary conditions. Does this boundary condition make sense? It's symmetrical at R equal to 0. And is this one? Well, that's our specified temperature. Now you just forget your aspiring mechanical engineer, your mathematician, you separate, integrate, you get the solution, and there's our general solution. What's that general solution look like? Linear, cubic, quadratic, exponential, hyperbolic sine, cosines, sinusoidal. It's just quadratic in R, isn't it? And then you can get the maximum. It's going to be at the center line, and you're ready to solve a bunch of problems. Here's a problem. You said, oh, let's just throw in some numbers for K, for the diameter, Q dot, surface temperature. You have the general solution, and then you would just calculate the maximum temperature at the center line, 139. I'm almost too embarrassed. It's just, once you have the equations, just plug in. But engineering is not plug and chug. A lot of people think it is, but it's not. And then you change it up and you say, well, we don't know the outside surface. We do know the fluid surrounding it, and we know a convection coefficient. How do I solve that problem? Well, just use Newton's law of cooling to get the surface temperature, and then use the solution that you just attained for the maximum temperature in a heat conducting rod. So we find the volume for 1 meter length of that rod, multiplied by the rate of heat generation per unit volume to get the total number of watts that have to come out of that rod, divide by the area to get the flux. So this is how many, 85,000 watts per meter squared. Yes, you can do that a little more streamlined if you like, but avoid errors. So I know that it has to be convected off at a surface. So we have the convection coefficient. We just calculated Q double prime. We calculate the new updated surface temperature. It's a little warmer than 80-degree fluid temperature. It's 89. Then we use the same equation to get the new maximum, 148 degrees C. That makes sense? So what we're doing here is when we have this energy generation, you could do it in a radial system, and then you can add to that resistant concept with it. So we finished this section. Next time we'll pick up with heat transfer with extended surfaces. Let me go ahead and stop. Thank you for your attention, and Zach's going to pass out a quiz.